May the force be with you. And that's going to be really important for today's lesson, which is AP Physics C Mechanics Unit 2, which is all about forces and dynamics. So today's objectives are going to be forces and dynamics, looking at Newton's laws, looking at normal force, the weight force, friction force, and drag force, and finally talking about what centripetal force is. So to start, let's talk about what force is in general. So dynamics is how an object moves in relation to the forces that are acting around it. And a force is basically a push or a pull on an object. And forces have both magnitude and direction. So for example, when we look at this box in the picture, we see that there's many different forces that are acting on this box. So for example, because of the force A, the box is going to move slightly this way. Because of force B, it's going to move slightly that way. C is going to make it move up, and D is going to make it move kind of to up here. And so it's because the forces have magnitude and direction that that objects in general are able to move in different ways. And so forces with a greater magnitude are going to push the object more, and forces with less of a magnitude are going to push it less. And also the directions are all going to be pointing it to different ways. So for example, because force A is pointing it to the left, the box will move towards the left, and because B is moving it to the right, it's going to move to the right. Now, with that, let's come to our next topic for today, which is free body diagrams. And because there's often many forces at different magnitudes and in different directions on each object, we have this thing called a free body diagram that's supposed to show all forces on an object. And so for the purpose of this diagram, we consider all forces to act at the center of the object. So for example, if you have this box being pushed on a surface right here, usually when we use dotted lines, or dashed lines like this, it means an object on a surface. So for example, if we have this scenario where a person is pushing the box on this surface, we would do this as a free body diagram. So this is the center of the object. And two of the most common forces that you see is on an object on a surface at least. One of them would be the normal force, which is a force that pushes from the surface, and that usually balances out the weight force. And the weight force is basically gravity. So it's the force exerted on an object because of its mass. So for example, here we see that from the center of the object, we have the weight force, which is pointing down because the object is being pushed towards the ground because of gravity. We have the normal force, which is being pushed up from the surface to counterbalance gravity, which is why it's pointing up here. And then we have the force from the hand. So you see how the hand is pushing it that way. We have that same force from the hand pushing the box that way as well. Now you'll notice that all of the arrows stem from the middle. So even though the hand is pushing it from this side, it's still pulling the box the other way. And so you would use all of the arrows in relation to what direction the box is actually moving. Now, how do we actually solve these problems? Now, to know that, we should look at something called Newton's laws. So Newton is this guy named Isaac Newton, and he defined most, if not many, of the laws of physics that we use in both kinematics, dynamics, in any unit that you'll see in AP Physics. And so the three main laws he came up with related to forces are the following. One, an object with no net force will have constant velocity and no acceleration. This means that if there's no active force pushing an object and it's just moving, it'll be moving with constant velocity. It could be 0, it could be 5, it could be 10,000, but it won't be moving with a changing velocity. Now, the second one is what's going to help us the most when solving a problem. It's the net force equals the mass of an object times the acceleration. And we'll see how this applies to problems in the future, but this is the basis of most, if not all, of the problems we'll be seeing in this unit. And number 3 is that if object A exerts a force on object B exerts a force of equal magnitude and opposite direction on object A. And this is probably the most famous one you might have heard of. It's like every action has an equal and opposite reaction. And essentially what this means, for example, in the case of the normal force and the weight force, is that the normal force and the weight force will cancel each other out. And that's because they're exerting a force of equal magnitude and opposite direction. Now, with that in mind, let's again zoom in on the second law because that's what's most important for our calculations. And so Newton's second law again states that the net force equals the mass times the acceleration. And so the way we like to write it in physics is through this. So this basically means the sum of, we use this notation. So the sum of all the forces equals the mass times the acceleration of the object. And because acceleration is a vector, we put this vector symbol on top of it, but usually you don't have to do like vector calculus or vector mathematics with the vector. We just call it a vector. So mass, we usually use kilograms, or we always do, and acceleration is meters per second squared. And so the units for this would be meter or kilogram meters per second squared, which we also call newtons. So let's just write that in. So it's usually going to be kilograms meters per second squared, and that equals a newton. And so usually when you would solve problems, you would use an N to describe this. And so usually also when you solve for forces, you split them into X and Y components. And what that means is you're going to solve for the sum of the forces in the X direction separately and the sum of the forces in the Y direction separately. Because oftentimes the acceleration in the X and Y direction will be different. If you're confused on what that means, make sure you check out the video on Unit 1 kinematics, especially when we talk about projectile motion, because sometimes acceleration can be different in both directions, and so we like to keep it separate for the calculations. So we already talked about this, but the first force we're going to kind of look at is the weight force. And again, the weight force is basically just gravity. So it always acts downward in the direction of gravity because gravity is always going to pull an object down, and it acts to balance out the normal force. So the way you would calculate that is the force from gravity, which we call mg, equals mass times gravity, and that's why we call it mg. And so if you didn't remember from our last video or from Unit 1, g represents the universal gravitational constant, and g is the gravitational acceleration, and we would always use like negative 9.8 in all our calculations. And so for this, we're just going to use positive 9.8 times the mass. And so mg is always kind of going to be the standard for weight force, no matter what it is. Mg will always be the standard weight force. So let's go into an example. For this example, we're going to be looking at an elevator. And so let's say a person is standing in an elevator that is moving downwards and slowing down. So what does that mean? If any of you forgot, that means that since the velocity vector is pushing down, because since the elevator is moving down, the velocity vector is also going to be moving down. And because it's slowing down as well, if you remember from kinematics, if velocity and acceleration are going in the opposite directions, that means the object must slow down. Which means in this case, because we're given it's slowing down and it's moving downwards, we know that acceleration is pointing upwards, which is why in this diagram, these are where the arrows are pointing. Now you see that there's a person standing in the elevator, and let's practice how to actually do a free body diagram. So in this one, we only have two forces. Remember up here, it was pretty complicated with three. Right here, we only have two forces, so it's just going to be the normal force pointing upwards and the weight force pointing downwards. And to do this, let's look at both the force balances because we're going to do both components. Now in this case, in the x direction, there's no force because as we look in a free body diagram, they're both going vertically and there's nothing going horizontally. And so the free body diagram or the force balance would be the sum of the forces of x equal the mass times the acceleration in the x direction, but that all just equals 0 because there are no forces. Now for the second one, it gets a little more complicated. Since there are forces, you have to say that the mass times the acceleration in the y direction equals the normal force minus mg. And the reason for that is you would subtract the negative vertical forces from the positive vertical forces. So you have, because in like the standard plane, our x's increase this way and our y increases that way, you would look at this as positive y and look at that as negative y. And so what you would do is you would take the positive y's and then subtract the negative y's, since that's how you would look at force, and you would say that it's n minus mg equals may. Now, if you get a problem like this on the exam or on some sort of problem sheet, you would have to be able to, it would usually ask you to solve for the normal force, and to do that, it would usually give you the acceleration of the elevator. And so usually elevator problems are pretty frequent on the exams. So it's really important to kind of let that sink in, like how to do the force balances and how to do all of that. Now, force balances obviously don't just exist in problems like these. There's many different forces that can be applied to a force balance that are all essential to know. Now, the second one is going to be friction force. And so friction force is a force exerted on an object when it slides across a surface. And this is usually like a rough surface or like, an uneven surface. And typically in real life, most, if not all, surfaces are like this. But sometimes in some physics problems, they might say, oh, it's a frictionless surface, and that just means you don't need to account for this. But in the case that it is a rough surface, there's two different kinds of friction. One is kinetic friction, which is basically when an object moves and it's experiencing resistance because it's moving across a rough surface. The second one is going to be static friction, which means like an object that's staying still because of the friction. Now, usually on the AP exam, you're only going to encounter kinetic friction, and this is the equation that is for it. So the kinetic friction, that's how you would write it, equals the coefficient of kinetic friction times the normal force. Remember, we already talked about the normal force, and so let's read the example. A 15 kilogram box is being pushed across a rough horizontal surface at an acceleration of 7.8 meters per second squared, and the coefficient of kinetic friction between the surface and the box is 0.12. What is the force pushing the box? Now here's a picture of the situation. The purple lines here kind of represent the friction. Usually on a problem, if you were asked to draw a picture of the situation, which usually you're not, you would use a squiggly line like this to represent a rough surface. Sometimes College Board might give a picture and it might have like a squiggly line. And so you should just know that means that it's a rough surface. So this is a picture. This is our free body diagram here. So we have the normal force, weight force, the force of the person pushing the box, and then kinetic friction always acts opposite direction of motion. And that's just a standard rule. And so when we look at this, let's start with the force balance in the x direction. So we're going to have the pushing force minus the friction force equals ma. Now, in this case, we can then simplify that using the f of k, or what that means, and that, remember, that means the coefficient times the normal force. So we have F push equals the coefficient, or F push minus the coefficient times the normal force equals ma. Now in this case, we don't know what the normal force is, and so now we're going to have to look at our y force balance. So we go to the y force balance, we set the normal force minus mg equal to 0 because there's no acceleration in the y direction. And then the normal force we get equals mg. And typically this will work in most cases, but sometimes there's going to be multiple forces in the y force balance. So just make sure you keep a lookout and don't just default to n equals mg. Now, when we plug that back in and solve using the variables, we're going to get 134.64. And you can feel free to test that on your own calculator just to make sure it works. So that's the first major force. This will usually be the most common force that you're going to see. But the second most common is probably tension force. So tension force is kind of a force from a taut string. There's no like formula for tension force. It's usually just sometimes used to balance out other forces in a force balance. So usually you'd see this in the context of pulleys, Atwood machines, etc. An Atwood machine is basically like a pulley, and the equation for that is on the equation sheet. And so for a question like that, you would just basically look at the equation sheet and copy that equation. But let's just go through an example problem just so you see kind of what kinds of problems that you would get with tension force. So, for example, a crystal chandelier with a mass of 45.3 kilograms is hanging from the ceiling by a rope. The chandelier is at rest. What is the magnitude of the tension in the rope? Now, as you see here, this is kind of a picture of the situation. Again, we have a surface here. This time it's on the top. This would be the string, and this is the chandelier. Now for the force balance, you would have the tension here and the weight force like this. Now it's really important here that it's hanging from the ceiling, which means it's not really moving, it's just kind of hanging there. And again, it says it's at rest. So when we do the y force balance, we just get T minus mg, again, T minus mg equals mass times the acceleration in the y direction. But since it's at rest, that means the acceleration would be 0, which means it's just T equals mg, and then you would just solve for mg using that times 9.8, and you would get approximately 444 newtons. Again, you can test that out if you're getting like the wrong calculation or if you just want to practice using the calculator. But typically the calculations with tension force are just similar to this. You would just have to calculate it in relation to the other forces. And it's mainly just trying to test your knowledge about whether you know the other forces and how to deal with tension force or not. Oftentimes, tension force will also be at an angle. And to solve for that, you would just multiply by the respective cosine of sine, which we will talk about in future videos and future lessons. And next, which is pretty uncommon, is something called drag force. Usually there won't be many calculation problems about drag force, but it'll mainly just be like conceptually like what it is. And so it's really crucial to know that drag force is basically the force a fluid exerts on an object. And a fluid can be a liquid, a gas, so it can be water or air. And so in this example, like, we have a fish in the ocean, and basically it's kind of like friction except in the water. So it acts opposite the direction of motion, and we refer to it as F of D equals D times V squared, where D is the drag coefficient and V is the speed. So it's kind of similar to friction force, but not really because of this V. And it's weird because it's dependent on the velocity. And so as you see here, as V points forward, FD points the opposite way. And basically the reason it's dependent on velocity is that when an object is in a fluid, whether that's air or water, velocity increases and acceleration decreases when the object is in free fall. So for example, when you drop an object off of a tower, because it's experiencing drag force because of like wind and air resistance, acceleration will decrease as it falls, but velocity will still keep increasing since acceleration is positive. But once acceleration eventually reaches zero, velocity becomes constant. If you're confused about that, you should watch our Unit 1 video. And essentially, after deriving the equation, you get that the terminal velocity, which is v of t, equals root mg over d. Again, d is the same d that we talked about there. And so a lot of the times they'll give you graphs. So for example, here, this is a graph of acceleration. So when you are experiencing drag force, the acceleration should kind of look like this. So it should start up here and then gradually decrease like that. And velocity should gradually increase and then become constant. And so that's the way it would usually work. Usually you won't be asked to do calculations. And if you are, it would just stem from this equation or from that equation. And sometimes you would have to solve for the force, for the drag force at terminal velocity. And in that case, you would just substitute v with v of t, and you would just solve for that. So usually these calculations aren't too complicated. It's mainly just conceptually. Now, last but not least, let's talk about centripetal force. Now, it's really important that to understand centripetal force, you have to understand uniform circular motion. And if you don't, again, refer back to Unit 1. I know I've been saying that a lot, but Unit 1 is really, really important, especially for something like this. So centripetal force is the force exerted on an object in circular motion, and it's in the direction of radial acceleration. Now, it's really important to mention, I put it in all caps because it's really important, that centripetal force is not actually a force. It's just a calculation that helps us calculate, many different variables that are involved with the circular motion. So we kind of treat it as a force, but it's not something that should go on your free body diagram. It's just something that'll help us solve for other variables. So for example, let's say there's a force let's say, there's an object going in uniform circular motion, and along the line of radial acceleration, so along basically the radius of that circle it's making, you would call the force that it's experiencing the centripetal force. And basically any force that the object is experiencing along the line of the radius can be solved using the mass times the radial acceleration. This might all seem like gibberish, but let's go into our first example, and that'll maybe help things clear up a bit. So a sled with a mass of 25 kilograms is tied to a pole in the middle of a frozen pond with a 5-meter long rope. Now let's stop there. The reason it's important that this is a frozen pond is because a frozen pond means that there's no friction. Now there's some keywords like that you should be aware of when you're doing the exam. If it says something is frozen, that means it's ice, that means there's no friction. And they might just throw that on just to make you remember that, oh yeah, this is frictionless, I don't need to use friction. So just be aware of that. So the sled travels in a circular path around the pool at a speed of 2.62 meters per second. Find the tension force exerted on the sled by the rope. Now, this is kind of the path of the object. So this will be the sled, and the sled is kind of moving around like that. And so at any given point, it has radial acceleration along the radius. And this is obviously the velocity vector. It's not really important in this case, but what is important is that this is the line of radial acceleration. And this is also the line, remember that it's traveling with a 5 meter long rope. And so basically there's this rope, this is basically the rope, and the rope is moving around like that. And that rope kind of represents the radial acceleration. And so the free body diagram only consists of one force, and that force would be the tension force. Because this is 3D kind of motion where technically you have a force pointing into the paper for weight force and pointing out of the paper for the normal force, but since we only have so many directions we can use on the paper, we're choosing to use the radial acceleration because it's more relevant to the problem. And we're choosing to therefore keep this a circular motion because it helps us understand it better. And so we're just looking at those two dimensions instead of the one going through the paper, if that makes sense. Let's move on to the force balance. So the force balance, we're going to be looking at F at like the sum of the forces in the X direction. Well, technically this is the Y direction, but it doesn't really matter which way it's oriented. So we're just going to call it X. So that equals the centripetal force, again, because it's on the direction of ARAD, it's moving like that. And so you would say centripetal force equals mass times ARAD, and again, centripetal force in this case equals the tension force, because they're both pointing in the same line of ARAD. So you have F of C equals T equals mass times ARAD, and if you recall the equations that we used for ARAD, one of them was V squared over R, and when you solve for that, you get 34.3 newtons. Now, this is a very basic overview. There will be a part 2 coming with more solution-based things. So we'll cover forces at an angle, banked curves, and things like that because unit 2 is so complex. But this is just a basic overview. So let's go back to the top and go over the objectives. So again, today we talked about forces and dynamics, and we talked about how a force is something that pulls or pushes an object, and how there's many different forces in different directions and magnitudes that can be on objects. Now, some of those forces were the normal force, the weight force, friction force, and drag force, and we used Newton's laws, and specifically Newton's second law, in order to solve for these calculations. Now, finally, we talked about centripetal force, which is kind of the force that's seen in circular motion, and that's all for today's version of Unit 2. And we're going to have a second part of Unit 2, which again will have more problems and more solutions, and more just little things that you would need to know. So thanks, and tune in for Unit 2.